Welcome to Math 31. This is a lesson on the derivatives of the remaining trig functions, tan, cotangent, secant, and cosecant. So currently we've got command, I hope, over sine and cosine, and from those, using those, we can derive the remaining derivatives. Now, all of these are going to be available on your formula sheet, so you don't have to memorize them, although I suspect for at least some of them you will probably file it away someplace. Now, starting with tan, so given a function tan x, if we were to get the derivative of tan, we'd want to recognize first off that tan is in fact equal to sine over cos. And that allows us to use the quotient rule to differentiate. So keep your formula sheet around right in front of you, and with the quotient rule we can see that u is equal to sine x. So in traditional form, u prime is equal to cosine x. And then v is equal to cos x. So v prime is equal to negative sine x. And as you recall, y prime, I hope, y prime is equal to u prime v minus u v prime all over v squared. So I'm just going to get a little bit more space to work and then finish this one off. So y prime, well, equal to u prime, so that would be cos x times v, which is also cos x, and then it would be minus u, well, u is sine x, times v prime, and v prime is negative sine x. All this is over v squared, and v squared is going to be cos x squared. So I'll write that as cos squared x. So therefore y prime is equal to cos squared x plus sine squared x, and this is all over top of cos squared x. Now you take a look at that numerator and it will occur to you, I think, that using a Pythagorean identity, cos squared plus sine squared is equal to 1, and then cos squared on the denominator, and then that's correct, but typically we'll write the derivative of tan x in a little more complex form, at least not in a non-denominator form. The reciprocal of cos squared is going to be secant squared x. So there we have it. That's how we differentiate tan. Now there's 5 or whatever of these 4, I guess, that we haven't looked at. I'm not going to derive all of them, but I'll do one more, which is a slightly different form, and then the other ones we can just sort of take them at face value. So if you're given the secant function and you want to get the derivative of secant, the way this one works is putting it in terms of a primary form. Secant is equal to 1 over cos, which you could write as cos x to the negative 1. And then using just the chain rule, we'd get y prime is equal to negative cos x to the negative 2 multiplied by the derivative of cos x. Now I'm going to go directly there. That's negative sine x. So therefore, y prime, the two negatives are going to cancel, and we have sine x, which has got a positive exponent, over top of cos x squared. Now, write it like this temporarily at least. And this, of course, is correct, but it's not compact at all. So we could write it in a better form of sine x over cos x, break it up, and then 1 over cos x. Now you're probably thinking, well, right away, of course, that sine over cos is the form you want it, because that is equal to tan. So y prime is equal to tan of x times, well, the reciprocal of cos is secant x. So therefore, the derivative with respect to x of secant x is equal to tan x times secant x. Now it means, of course, that if you want to get the slope of a tangent line to a point on the curve of the secant function, then you take that x value for the point you want, substitute it into the tan, or take the tan of it, take the secant of it, and multiply together, and then you've got the slope. So it's not necessarily straightforward depending on the value, but that's how it would work. Now the other ones work same way basically. To get cosecant, you just go take the reciprocal of sine and differentiate that. And to get cotangent, you go cos over sine. So there's really no value in looking at those ones again. But here is the list of them all, and as I said, they are on your formula sheet. The derivative of secant we know to be tan x secant x. This you didn't know before, but the derivative of cosecant x is equal to negative cosecant x cotangent x. If you don't believe it, derive it yourself with 1 over sine. And then the derivative of cotangent x is negative cosecant squared x. Same thing, go cos over sine if you are curious. And then the derivative of tan, as we saw earlier, is secant squared x. So keep these around in front of you. And a few other observations that make it easier to remember these is that the derivatives of the c function, so anything that starts with a c, these will be negative. So cosecant, the derivative of cosecant is negative cosecant cotangent. The derivative of cotangent is negative cosecant squared. And even the derivative of cos is negative sine. So that might help a little bit. Not really that mission critical that you get that down because you do have a formula sheet, but for your information. So let's go through a few derivatives and see what we can do with these. As always with the trig ones, it's really a matter of just being very, very careful. Because you're using these set forms for it, there's not an awful lot of room for improvisation. You just very carefully go where you're supposed to with them. So to differentiate the following, first off, let's take a look at a tan. Now I would encourage you for any time you have an exponent around the entire function, I would encourage you to write it in a more conventional bracketed form like this, because then it's a little bit easier to do the chain rule. Now, of course, it's not necessary, but most people find it easier, at least at the start. So this becomes 3 times the tan of 6x to the 2 multiplied by the derivative of tan 6x. Now, the derivative of tan 6x working down, according to what we just learned, is equal to the secant of 6x squared. Now, I'll put it in a bracket form like this for now. But then we have to multiply it by the derivative of the inner, which is 6x. And I think that most of you will not go through all these steps when you're differentiating something like this, but this is what your brain is doing. So this is the secant of 6x squared multiplied by 6, and then this is times 3 tan of 6x squared. Now putting this in a better form, the derivative of y with respect to x. Now be really careful. This is 3 times 6. It's 18. So you multiply the numbers together, and everything else is being multiplied together. And then we have tan. I'm going to put this back in the normal form, tan squared 6x multiplied by secant squared 6x. Now you could look at this and see, can I do anything more with it? And the answer really is no, because there's no real formula that's going to simplify tan and secant. So you pretty much are stuck with the way you have it. You could write that as tan is sine over cos of 6x all squared. Wouldn't really do much for you, I don't think. So we're left with this. Let's try some other ones. Now, another point on this before we do go on is the use of brackets. I use brackets when I'm simplifying them, but if I have any doubt about what belongs to what, I put a bracket around, and having too many brackets is not a serious thing. But you really have to be careful about when are you multiplying and when are you like taking the argument of. So we'll see that in a little bit again and get another look at it. Now this is cotangent cubed 3x plus 1, so that's not a big deal. Cotangent of 3x plus 1, like this, and all this is being raised to the exponent of 3. So clearly it's a chain rule situation. So y prime is equal to 3 times cotangent of 3x plus 1 to the 2 multiplied by the derivative of cotangent of 3x plus 1. Working our way downward, take a look at what we know about cotangent, and according to our formula sheet, that's equal to negative cosecant squared of the argument. So this becomes negative cosecant squared of 3x plus 1. So I'll put a bracket outside the whole thing, but you don't have to. You could tuck it in and you'd be fine. And this would then get multiplied by the derivative of the inner, 3x plus 1. So feel free to combine these steps. It's just that this is pretty much showing everything. So the derivative of the 3x plus 1 is 3. That will be multiplied by negative cosecant squared 3x plus 1. So I'll write it like that. And then this comes down, the original first stage of the differentiation is 3 multiplied by cotangent squared 3x plus 1, and then that's times this. Now obviously we can do a little bit of simplification of this, dy dx. We have a 3 times a 3, and actually a negative, so that's negative 9. And then the order doesn't matter, but it's going to be cotangent squared 3x plus 1, so got the exponent back where it was, multiplied by, so I put a dot for multiplication, but that is optional, multiplied by 3x plus 1. And there we have it. It's not difficult, but you must be careful with it. Number 3, x squared times cosecant of 5x. Now this one is going to require us to, because we're multiplying these two terms together, we're going to have to use the product rule. Now your choice, of course, with the product rule is always, do I take it to the side and work it out, or do I just go through it? And, you know, both are okay, but the sort of way I approach it is if it is like a little bit more of a complicated term, if it's something other than basically just x times y or a times b, I will take it to the side. And in this case, it's probably a good idea. Like u is equal to x squared, so u prime is equal to 2x. And then v is equal to cosecant of 5x. So we take a look at cosecant and how to differentiate that, and it becomes negative, according to what we see there, cosecant x cotangent x. So negative cosecant 5x times cotangent 5x. And then this is going to be multiplied by the derivative of the inner, which is 5. So we have to use the chain rule on it. Now, the way you'd write that otherwise is taking the 5 to the front. So negative 5 cosecant 5x multiplied by cotangent of 5x. So always be careful. This 5x is not being multiplied by the 5. And if you have any doubt at all when you're doing it, put a bracket up around it so it's perfectly clear. You don't want to make a mistake on that, because if you make a mistake with it, you don't find the mistake. Never shows itself up, or never shows up. So y prime for product rule is u prime v plus u v prime. So in this case, y prime is equal to u prime 2x times v, so that's cosecant of 5x, plus u, which is x squared, times v prime. Now that's negative, so I'm going to take the negative 5 and write it in front. So negative 5x squared cosecant 5x multiplied by cotangent 5x. And the only thing that I think we can really do with this one now is to deal with that negative, that plus a minus. So dy dx is equal to 2x times cosecant 5x minus 5x squared cosecant 5x cotangent 5x. And always take a look, see if you can do anything else. And, you know, of course, the temptation is to take that cosecant and write it as 1 over sine, and cotangent as cos over sine. And it's not wrong to do so, but it doesn't go anywhere because there's no simplification, and that's the way it works with the cosecant and the secant ones. Even though the derivatives give you two functions, they do not combine. If they did combine, that would be the common way to express them. So there we are with that problem, and then let's move on to a slightly different variation. This is going to be a chain rule problem. We've got y is equal to sine x, sine of 5x minus cos to the 5x. Now, this one is interesting because I'm not going to use a substitution with it, but it is tempting to go y is equal to u to the 5. Remember, substitutions can be used at any time. It's just a question of, it's never wrong. It's just a question of whether it's worth doing or not. So making a mistake by using a substitution when it's not necessary is not a mistake at all. But anyways, I'm going to not use a substitution for this one. I just go dy dx and then go the chain rule. So 5 times the sine of 5x minus the cos of 5x to the 4 multiplied by the derivative of the inner. Now again, I'm going to write this. I'm not sick of it yet. I just don't want to make a mistake with it. So the derivative of this minus the cosine of this. And then I take this down. Now those are not too bad because in fact this one is just regular sine and cos, which we've done more of in the previous lesson. The derivative of sine 5x is cosine 5x and then times the derivative of the inner, which is 5. So I'll put the 5 there right away. The derivative of cosine 5x is negative sine. So negative becomes plus and then sine 5x. Not forgetting, though, that we have to take the derivative of the inner. So we get 5 cos 5x plus 5 sine 5x. Now all this has to be multiplied by the original, or by the first stage of the derivative, not the original. So we get 5 times sine 5x minus cos 5x to the 4 multiplied by, now when you take a look at this next one, you're probably thinking, as am I, that we can factor out a 5. And then that will give you cos 5x plus sine 5x. So dy dx, now 5 times 5 is 25, and then sine of 5x minus cosine of 5x to the 4 multiplied by cosine of 5x plus sine of 5x. And there we have it. Okay, so that's number 4. Let's take a look at a few more. Y is equal to the sine of root x plus root sine x. So this one, just a different form of everything that we've seen up to now. So sine of 1/2 x. So everything works the same, but they just look a little bit different. And you can see that this is the derivative-ready way to write it. So we put it in exponential form. There too, for the second term, I wrote that as sine x to the 1/2. So these are ones that look similar, or the terms look similar, but they're not identical. Dy dx is equal to, well, the derivative of sine x to the 1/2 is cosine x to the 1/2 multiplied by the derivative of the inner, which is, okay, let's be real careful with this. The derivative of the inner is, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. So I didn't bother writing the d dx. Now it's a judgment call, but I hope that worked out for us. And then the next part is 1/2 sine x to the negative 1/2, and then we multiply by the derivative of the inner, which is cosine of x. Now we would, if that was anything other than x for an argument, we'd have to take the derivative of that as well. But we don't need to because there it is just x. And now we see what we can do with this. It certainly can be cleaned up a little bit. The cos x 1/2 can be written as cos. Now you could keep it as x to the 1/2, but I'm going to put it back as a radical. Root x. The 1/2 would be 1 over 2, so the 2 goes on the denominator, don't need to put the 1. And then x to the 1/2, negative 1/2, is square root x on the bottom. And then this one, sine x to the negative 1/2, is cos x on top. The 2 goes on the bottom, and we have now the square root of sine x. So x to the negative 1, sine x to the negative 1/2. Don't forget, this is dy dx. So now let's move on to number 6. Now this one is cosecant of cotangent 4x. Now really important to remember with these that you are not multiplying these together. This is not a product. And that's one of the common mistakes. This is not cosecant times. This is cosecant of cotangent 4x. So cotangent 4x is the argument. And it's important to remember that because by looking at it, sometimes you can get mixed up with these. Now, this is a good example of where a substitution would be helpful. Not necessary, but I'm going to use a substitution just because I don't like the look of having too many of these trig functions around until the very end. So I'm going to let u be equal to cotangent 4x. Had you let u be equal to 4x itself and only that, it still works out, but I don't think you get as much value from the substitution as we will this way. So now du dx, you could go u prime, but I typically just use the u prime if it's the quotient rule or the product rule. When I'm doing the chain rule, I keep it like this, so I'm clear with the variables. Du dx. Now take a look at your cotangent 4x, cotangent, and then you'll see it's negative cosecant squared 4x multiplied by the derivative of the inner, which is 4. So du dx is equal to negative 4 and then cosecant squared 4x. Now I didn't use put a bracket around the whole thing, cosecant 4x squared, just because it was just to the exponent of 2. It wasn't really going anywhere. So that's probably safe. And then this expression really is y is equal to cosecant of u. And that makes the differentiation quite easy because dy du would be just the derivative of cosecant. Now dy dx is going to be equal to the derivative of cosecant u, all right. So we see that that's equal to negative cosecant u multiplied by cotangent u, but then also times du dx, the derivative of the inner. So that's using the chain rule properly. So dy dx is equal to, well, negative cosecant of u, which is cosecant of cotangent 4x, multiplied by cotangent of u, which is cotangent of cotangent 4x, then multiplied by du dx, which is negative 4 cosecant squared 4x. And now it's just a matter of writing it out in as simple form as we can. Now I see two negatives being multiplied together. So that's going to be a positive, and then bring the 4 to the front. Now the order doesn't matter otherwise. I'll just keep it the way I've got it. Cosecant of cotangent 4x. Good idea to have that bracket around there. Multiplied. You don't need the multiply sign, but I've got it there anyways. Times cotangent of cotangent 4x. And then multiplied by cosecant squared 4x. And I think we've got it. So let's take a look at this question. Nothing outstanding happening with it except for the fact that it will be implicit differentiation and it will be the product rule. So we'll break that xy down. Derivative of x is 1 times y. So I'm not taking the product rule off to the side, just keeping it where it is, and then plus x times y prime. So the x stays the way it is, and take the derivative of y, which is y prime. Now the derivative of tan y squared is secant squared y squared. And then times the derivative of the inner, which is 2y y prime. And then that's equal to the derivative of x, which is 1. Now get your y prime terms together. I'll keep them on the left. So xy prime plus, I'll write it like this, put the 2y in front, and then secant squared y squared y prime. And that's equal to 1 minus y, so the y comes over. Factor out the y prime, and we get x plus 2y secant squared y squared. And that's equal to 1 minus y. And then to finish it off, dy dx will be equal to 1 minus y divided by x plus 2y secant squared y squared. That bracket is not necessary around the argument, but I put it there anyways. So that should take care of these type of problems. Next lesson we'll be looking at some graphing. Thank you for your time.